Okay. Chris and I would like to walk you through how we run Hive at Yahoo scale. So specifically, we're going to be covering the problems and challenges that we faced running Hive 13 in production. A quick round of introductions. My name is Mithun. I'm a Hive engineer at Yahoo and a committer at the ASF. There's a list of things there that I've worked on and how to get a hold of me should you need to. Incidentally, in the picture is my childhood hero and continuing role model, Gonzo the Great. So presenting with me is this modest gentleman. He is Chris Drome. He is a Hive engineer at Yahoo and a Hive contributor at the ASF. He is also, from the looks of it, a Monty Python fan. I'm told that condition is incurable. Let's take a quick recap now of how we got here. So at the last Hadoop Summit, I presented a talk, which was met with the reserved enthusiasm that this summit is known for. So at the talk, I presented some benchmark results from some tests that we've been running at Yahoo for a little time now. So we took different versions of Hive, starting from Hive 10 through Hive 13, on various permutations of execution engine, file format, data size, and so on. We ran TPCH, and we published our results. Now, this slide shows you TPCH at the 1 terabyte scale. It is representative of all the tests that we ran. So the result was pretty much unanimous. Hive 13 on ORC, on Thais with ORC and vectorization enabled, beat the proverbial pants off of prior versions of Hive. In some cases, the performance approached 20x. There are several reasons why. And you've probably heard some of these. So running with Thais, you get a more expressive physical query plan in the form of a general DAG, so you're not shoehorning things into MapReduce. Couple this with intermediate data, which doesn't touch the HDFS, and container reuse. And generally, Thais makes Hive really fast. Now, add to this mix the fact that Hive now has better table and partition statistics, vectorized execution, and the org file format. Which org file itself is pretty fast because of predicate pushdown, selective deserialization, so on. So right. The entire package was very compelling for us to push to production. So going to production, what do we expect? So we expected that Thais would continue to beat MapReduce by miles, or for the same level of performance, we expected better cluster utilization because Thais would require less resources to deliver that performance. 3, Thais would be quote-unquote production ready, which means it would support GUIs for job tracking, debugging, and so on, as well as ideally speculative execution. And finally, ORC and vectorization would be able to support real-world nuisances like schema evolution. Now, all of this is theory. I'll let Chris talk to you about what happened when we pushed to production.
Thanks, Mithun. Oops. Okay, so I will introduce to you what Hive on Thais means at Yahoo. So let's start by examining the makeup of our grid at Yahoo, and then talk about some of the issues and challenges that we faced when we began to roll out Hive to sort of a wider audience at Yahoo. Yahoo has 18 different clusters, and these are categorized as either sandbox, research, or production. And the corresponding hardware footprint for these is over 40,000 machines. Our largest cluster consists of more than 5,700 machines. As a whole, the grid processes over 1 million jobs per day. We manage a wide and varied collection of data sets, and while most of these data sets are updated on a daily or an hourly basis, there are some data sets which are being updated every 15 minutes or even every minute. The scale and update frequency of these data sets, in conjunction with their respective data retention policies, can lead to tables with literally millions of partitions, which consist of potentially hundreds of different part files. This results in terabytes of data for just a single table. Aggregate counts are on the order of close to 600 petabytes worth of data that's being managed across all of our clusters. And each cluster provides a set of gateway machines where client libraries such as Pig, Oozie, and Hive are made available to all of our users. So let's examine the grid usage numbers in a little bit more detail. I mentioned to you that the grid processes more than 30 million jobs per month. So the majority of the data pipelines and ETL processes at Yahoo use Pig, which accounts for roughly 43% of all the jobs that are processed on our grid. If you discount the Oozie launcher jobs from this total, it amounts to an even larger number, somewhere around the neighborhood of 65 to 70% of all jobs. Compared to Pig, Hive plays a very different role on the grid and targets a more sort of specialized use case or specialized niche. We average more than 600,000 queries, and that's queries, not jobs, that are executed on a monthly basis, of which currently roughly 35% of those queries are being executed on the TES execution engine. So finally, we have HCatalog. And this is sort of you can think of it as being the glue which facilitates a coexistence between the various Hadoop ecosystem components. You can visualize or think of Pig as being the mechanism by which data is made available for analysis by Hive. So let's consider the role that Hive plays at Yahoo. Although Hive is certainly not restricted or solely used for BI tool purposes, it does play a very important role in facilitating the work of data scientists and analysts at Yahoo. So we offer support for users of Tableau and MicroStrategy to run various ad hoc queries or analyses via Hive Server 2. And there are also teams who deploy their own Tableau server, which allows them to consistently and periodically run jobs that produce suites of reports. As you might expect, nothing is ever quite so simple or easy as you first imagine. So when we first tried to introduce Hive Server 2 to our clusters, we encountered a number of challenges that we had to first address. And these ranged anywhere from opening up the correct ACLs for our users to enabling Kerberos authentication and ensuring that the data was encrypted before it was sent over the wire. So once we resolved these, we got to the next set of issues that users began reporting. And this comes about as a result of how Hive Server 2 works or is designed. So Hive Server 2 facilitates JDBC and ODBC clients over a thrift communication protocol. So given the performance limitations of early implementations of this protocol and the scale at which we run at Yahoo, we were sort of concerned that this was a problem in the making. So we added a little bit of code that would disallow or block queries that attempted to access an excessively large number of partitions on very large tables. We also embarked on a campaign of trying to educate our users about best practices for using Hive Server 2. And this included such things as making sure that the size of your result set did not exceed, say, tens of thousands of records. And also encouraging them to generate aggregate counts as opposed to streaming the raw data to their clients, which was also a concern for our legal department. So these efforts had been largely successful, and they led to the next set of challenges for us, which were primarily performance related. So we addressed many of these issues in code by optimizing, for example, the HCatalog server to answer queries that were metadata only type in a much more timely fashion. For other types of issues, we worked directly with teams and individual users to help them rewrite and optimize their queries in such a way that they would be able to avoid some very costly operations such as full table scans. And finally, we demonstrated to our users that materializing their views does have a great performance benefit for them. So while considering the upgrade from Hive 12 to Hive 13, we identified a number of items that were more or less sort of non-negotiable for us. And I think Mithun has already touched on some of these, but I'd like to go over them once again. So for us, Hive would have to work in a heterogeneous environment where data could and would be registered by any number of machines. And this is not just Hive or pig jobs that would be generating and registering the data. Furthermore, the data would have to be owned by the producer of the data, who would also control access to the data via HDFS file permissions. So we would have to make sure that we respect those. Then consider our HCatalog service. We would have to make sure that this was robust, resilient, and most importantly, highly available. Regarding TES, we wanted to ensure that we had a UI that would allow users to track job progress, view configurations and counters, and most importantly, be able to access task logs, which would facilitate in them debugging their jobs. And finally, it was our hope that TES would be able to support speculative execution in the same way that MapReduce did. So, given these expectations, we embarked on our journey to build and deploy Hive 13 at Yahoo. At the time, we had Hive 12 deployed on all of our clusters, but we were really excited by the potential gains that Hive 13 on TES would bring to the game. So we started by evaluating both Apache Hive 13.0 and shortly thereafter, Apache Hive 13.1. Our first step was to backport, or I guess port forward, all of the internal patches that we had applied to Hive 12 onto Hive 13.1 branch. And then we made an alpha release available to early adopters for testing purposes. So based on our dev testing, as well as feedback from these early adopters, it became pretty obvious to us that this build was just not quite ready for prime time yet. So we began backporting various issues to fix problems that we were encountering. For example, we backported a number of issues that addressed TES compatibility issues. And this allowed us to build against newer versions of TES. And at the time that meant TES 0.5, TES 0.6. Then we backported a number of JIRAs that fixed NPEs and some other programmatic failures, and addressed a number of other data integrity problems. And then there were a set of JIRAs that fixed some issues with ORC file format and vectorization, as well as providing numerous optimizations to both of those. So the list that you see here is just a small part of the JIRAs that we ended up incorporating into our build, and is by no means an exhaustive list. In fact, Our first real candidate that we had for wider distribution at Yahoo consisted of some 285 JIRAs that we ended up porting from the community into our build. And subsequently, we've had two other phases where we've backported a number of important or interesting patches from the community in order to stabilize our build. So this gives you a little bit of an idea of what it took to build and have a candidate that we could deploy for wider scale, deploy at a wider scale at Yahoo. So given this stable Hive 13 build, let's examine what a typical cluster looks like today. So our hCatalog service typically consists of 2 to 4 machines running hCatalog server on hardware that is typically 96 to 128 GB worth of memory, and this service is backed by an Oracle rack. A typical cluster would have a collection of machines which are gateway machines, and these would contain Hive and Oozie and a number of other user libraries. Generally, our users would log into one of these gateways and launch their queries via Hive CLI. And finally, we deploy a number of machines, 4 or possibly more, which are dedicated to Hive Server 2, and they address our BI tools integration and any sort of JDBC and ODBC specific applications that we have running at Yahoo. So how did we get to this type of a configuration? Initial deployments consisted of Hive CLI running on gateway machines talking to a single instance of hCatalog. As more groups began registering their data sets with hCatalog, we had to ensure a highly available service. So we introduced multiple machines we added multiple machines to our hCatalog service that were behind a hardware VIP. At about the same time, we were looking to provide a solution for BI tool integration. So we had another set of dedicated machines running Hive Server 2, again running behind a hardware VIP. With larger and larger data sets being managed by our hCatalog service, we had to address the issue of HA on our Oracle as well. So we migrated to an Oracle rack. At this time, we were beginning to play with or manage larger and larger data sets, and we were starting to run into memory issues on some of these larger data sets. So we augmented the memory in our hCatalog machines to the configuration that I mentioned. Finally, and most recently, we've begun to introduce a dedicated service which runs Hue, and that gives our users sort of increased usability by providing them an interactive UI to interact with the Hadoop component stack. So the next big hurdle for us at Yahoo is to promote the wider adoption of org file format. In the process of doing this, we worked with some teams who are managing and producing some really very large data sets, and we started to encounter a couple of issues that we hadn't seen before. The first issue that I'd like to talk about was sort of a performance-related one, whereby queries on large data sets seem to be running a little bit slower than they should have on TES. So we did some investigation and brought to light the fact that there was a relatively expensive operation being performed inside the loop that ran over the records. So there was already a JIRA that addressed this issue in the community, so we backported that and resolved that issue. So having addressed this performance issue, we noticed that there were some queries, again, on extremely large, very large data sets that were just taking a long time to actually launch the jobs themselves. So after investigation, we found that split generation on these very large tables was actually the problem. It was taking a long time. The interesting thing was that it was tables that were using or backed by the org file format. So again, doing a little bit of experimentation, digging in and looking at what the state of the art was in the community, we found a series of JIRAs that were already addressing this issue. So we backported a large chunk of these JIRAs to address that problem, and we are currently testing those and experiencing, I can happily report that we're experiencing very good performance gains after applying those patches. So the third item that I have here is the ATS, which presented a few challenging issues for us. So although we didn't really experience the number of problems that say Pig did when they tried to integrate with ATS, we still did see problems with some queries that were being run on very large data sets. So for example, if you launched a job that tended to launch, let's say, tens of thousands of tasks, we found that there was significant pressure on the AM as well as the ATS. So if you dug into what was happening here, you would see that the AM message queues were sort of being overwhelmed, and the AM was unable to recover from this situation. And in the worst case situation, it would result in OOM failures. We were able to work around this for the most part by tuning memory parameters and various other AM configurations. So it turned out to be not as big of an issue for Hive. So now, before I hand back the presentation to Mithun, I'd like to plant a seed for you to think about. So there's many discussions and opinions around execution engines. So whether you choose the red pill or the blue pill, there's one thing that you really shouldn't forget in this whole discussion. And that's what happens when your execution engine doesn't perform as you expected, or saying it maybe a different way, what helps to make an execution engine run fast? So let's recall some of the numbers that we've already talked about and see if we can see what's happening here. So we have a cluster, and a cluster has, let's say, 100 databases at Yahoo. And each one of these databases has, let's say roughly 100 tables. And each table schema consists of anywhere between 10 and several hundreds of columns and is often partitioned. So in addition to this, each table can manage thousands or even tens of thousands of partition add requests on a daily basis. And given our data retention policies for most tables, this can result in as much as tens of millions of partitions and corresponding data. So this amounts to really a lot of metadata that we have to handle. And just to emphasize, you really need to pay close attention to all the decisions that you make in your design process. So I'd like to hand back to Mithun, and he will conclude our presentation.
Where's the pointer thingy? Yeah, there we go. So, okay, so Chris is kind of primed you guys to think about metadata as a problem at scale. Now, in the section that follows, I'd like to present some common problem scenarios that we have faced, the users have faced at Yahoo. We present these as letters written by our brave soldiers in the trenches to us for backup. The names in these letters are made up, but the problems are very real. So let's take the first one. So we have a user who complains that a query fails because it's run out of memory. Now, presumably this is because a reducer is being overwhelmed by a skew, so you bump the container size. Unfortunately, it still fails in the same way because although the container size is bumped, if you look at the settings, the heap size is not. So this is common, at least for novice users. So what you'll end up with is not only is the user not consuming 3 gigs per container, those 3 gigs are now being denied to everyone else on the job queue. So at Yahoo, we suggest that the heap size be set to 512 megs less than the container size, and those 512 megs will account for the overheads of Hadoop, the JVM, and so on. Simple, too simple. Let's take another one. So we have a user who complains that a custom UDF that he's written, for some reason, causes the queries to fail with timeouts. It turns out that the UDF was making a web service call. So again, novice user. So to spell it out, because his table was so huge, and because a UDF is evaluated per record, he had billions of calls to his web service across tens of thousands of mappers. So in effect, a distributed denial of service to his web service brought to him by Hive and MapReduce. So yeah, again, these are common problems for the novice. And again, it's because, so we can blame them a little bit, but you have to realize that Hadoop and Hive are kind of complex systems. Getting the configs lined up nicely is not terribly easy for the user. Okay, neither of those examples was sort of rock and roll enough, so let's take probably the most interesting one. So we had an ETL team contact us at Yahoo. Now, they were in the process of designing this massive table. It was soon to be the most popular table at Yahoo. They had 6 partition keys, one of which is an hourly timestamp. The combined cardinality would produce 10,000 partitions every hour, or 250,000 partitions every day. Now, even if you run a very simple query on a table this size, you land up with out of memory on the client, if you're lucky, sometimes in HCatalog. So please help. Now, this is a classic example of the impedance mismatch between, on the one hand, the amount of metadata we're trying to have at Yahoo versus what Hive could deal with efficiently. Now, a quick refresher. So when a Hive query is submitted, so Hive parses the query, constructs an AST, queries the metastore for partition information, which is HDFS path, deserialization info, and so on. And then it constructs a physical query plan, which is then optimized and executed using MapReduce or Thales or whatever. Now, one such optimizer that runs is called the partition pruner, which is responsible for tossing out partitions that aren't selected by the partition predicate. So in effect, it reduces the amount of data that needs to be processed. The sad thing about the partition pruner is that until recently, it would run in the client process as a single thread. Now, when it's dealing with 250,000 partitions, and each partition is pretty heavy, that's a lot of processing to do, which is why the client would run out of memory. Now, it is sort of, it is tempting to tell the user to reduce the number of partitions they have in the table. That's kind of like Steve Jobs telling you how to hold your phone. So we wanted to sort of meet them halfway on this. The code needed fixing. Now, before I go on, I will mention that the Metastore hardware is pretty beefy at Yahoo, but throwing hardware at it is probably not the most interesting part of the problem. It's what we did in software. So over the years, we have fixed memory leaks in the Metastore process, in Hadoop, in the Thrift layer, in Thrift itself, so that the Metastore process could have a larger uptime. So that was one. And then we reduced the CPU load by moving client processes such as Uzi to an event-based model instead of polling. So when Uzi wants to know which partitions are available in a table before launching a workflow, it can now listen to JMS notifications instead of polling hard on the HCAT server. So that reduces load a little bit. So the next thing we turned to was metadata-only queries, such as this one. If you want to select the distinct partition keys within a table, you should be able to do that. You certainly should be able to do that without a full table scan. Ideally, you should be able to do that even without a full partition list. You should be able to solve it using partition names. And that's kind of what we did. Work has gone on in community. Hortonworks has done some work. Special shout out to Selena Zhang from Yahoo, who worked on this a lot. She might be lurking among you. I don't see her. So I spent a little bit of time optimizing the optimizer. So the problem was there were some optimizers in Hive which would, as a first step, list all the partitions in a table. And that's like millions of partitions in our case. So the optimizer was getting in the way of performance. We avoided things like this, particularly for metadata-only queries, because you shouldn't need your partition list to solve it. So after fixing metadata-only queries, we turned our attention to sort of the metadata fetch part of things. So Sergey from Hortonworks introduced a framework by which you could insert direct SQL so that HCAT can talk to MySQL in the backend without using data nucleus. Data nucleus is a performance bottleneck at the scale that we run. So once again, Selena spent a bit of time tuning this to work under wider use cases, as well as to work properly with Oracle. And then in the meantime, I spent a little bit of time tuning partition info load over thrift. You see, if you query for partitions over the span of a day, it is very likely that of those 250,000 partitions, the column schemas are likely to be the same, as is the data format, the classes you need for deserialization and so on. So by suppressing the repetition of this information, because it's redundant, by moving it into a common place, we were able to reduce the payload over thrift by a factor of 25x, which allowed the jobs to kick off in 10 times less the time. So quite a bit of work has gone into the metadata layer. Excuse me. So now before we go on to the final letter, I wonder if you've heard this line before. The finest trick of the devil was to persuade you he does not exist. You might have heard this in Usual Suspects. Verbal Kint uses this to describe Kaiser Soze. Or you might have heard this in Sherlock, where Moriarty's work is described in this way. The line was actually written by Charles Baudelaire, who's a French philosopher, Lovecraft translator, and so on. The finest trick of the devil was to convince you he doesn't exist. Let me illustrate. A friend of mine, a long time ago, tried to convince me to quit writing code in C++ because Java is superior. Why? Java has no pointers, because of which you don't need to think about memory allocation, and Java cannot have memory leaks. We aren't friends anymore. But so now we're seeing this devil's trick here rear its ugly head again. It is a common misconception that to consume data off of HDFS, all you need to know is SQL, because now you have Hive. You don't need to think about mundane things like Hadoop or Hive or HDFS or MapReduce or Thais. I'd like to correct that notion in this final letter. See if you can spot that streak here. So a non-trivial user of Tableau Server at Yahoo, and we have several, complains that connecting Tableau server to Hive causes a the performance is less than stellar. And he's pretty sure that the query is okay, because it does run, it's just very slow. So please help fix Hive for this. Now, if you look at his query, that is the partition predicate that he uses. If you notice that the predicate is actually a runtime function. Recall again, the partition pruner runs during the optimizer phase, a priori. And because you're using runtime functions, it simply cannot play, which means this leads to a full table scan. It gets worse. They were using text file data on HDFS because it's easy to read by a human. Go figure. Two, they were using a lot of partition keys under the assumption that partitions are like database indices. So the more you have, the faster you must be. But it produced too many partition directories with too little data on HDFS. And three, even within each partition directory, they had way too many part files, which were very, very small. Too many of them. Think of the name node calls and the data node calls for the sake of processing these. Now, excuse me. So by eliminating the partition keys that did not contribute to the query, and by chunking all the part files together to larger chunks, and then switching them to a columnar storage, in this case, orc, 10x performance, right there. And this is with the full table scan. So if they were to switch to a compile time constant in their partition predicates, it would be even further reduced. The reason they couldn't, I think, was because Tableau server gives you no way of text substituting inside of like a template query. So if you were to do this in Bash, that's a whole lot easier to do. So that's the final letter. So there in the letters, I'd like to mention that there are still a bunch of things that we would like fixed or would like to work on. So you've probably heard the Thayes ATS scaling problems that John referred to in his talk yesterday. So that's one. Chris mentioned the split calculation could be faster at our scale. We want to put in a little more work in, excuse me, in detecting accidental abuse of grid resources by novice users. We would also like to work on get skew joins going in Hive and fixing Thayes' issues with native library detection. Because we often use crypto libraries and things which at the moment are not ideal in how they work with Thayes. So with that, and a minute left, I yield the floor for questions. Ask me. Okay. So is the question the performance difference between Hive 13 and 14? Okay, we're not exactly running 0.13, to be honest. So like Chris was mentioning, we pull patches from a bunch of places. So I would call our version of 0.13 more like 0.13.9, because it's very close to 0.14. But all we don't have are like ACID, we don't have that, and CBO. Cost-based optimizer is one thing we don't run. But those are the two things that you're watching out for when you go to 14.
So is there any reason why actually not updated 0.1?
We're working on it. So we're actively evaluating Hive 14.
The other question is, in practice, like, how much do you think approximate query answering will? Assume we bring these type of conditions to Hive. How much of your user can enjoy it and be totally fine with 99% accurate for their answer?
Right. So we were just sort of talking about this at lunch, and I think the BlinkDB solution or that type of approximate answer would fit in great with the Hue solution that we provide. So users would interactively launch jobs through Hue, and they would be able to see partial incremental increases or incremental completion of their job, and then they would be able to kill it when they get to within a particular error range. So I think that's an interesting idea to pursue.
We're out of time. Please feel free to ask us after the cameras are turned off.